Please go ahead.
Thank you. So, as he said, FEniCS for solid stresses to couple to CFD software for spallation target modeling. So to start with, a little bit about me. My name is Jessica Gould. I'm working as a computational scientist industrial placement student in the scientific computing department at the STFC, which is in the UK. I am still doing my undergraduate integrated master's degree, which means that in September I'll be returning to Bristol to finish that off. So a little bit about what I'll be talking about today. I'm going to introduce ISIS and talk a little bit about what is TS2, give you some of the ideas about my project aims, what it's been like modeling stress with FEniCS, some of the steps that I've gone through, and give you a bit of an idea of my next steps and the long-term vision of this entire project. So what is ISIS? ISIS is a spallation source. It's in Oxfordshire. What happens is that we get beams of protons sped up to about 80% of the speed of light in an accelerator and then shot at these two targets. When they reach the two targets, you get a lot of neutrons come off, and those neutrons are used for measuring material properties on an atomic scale. And these have applications in engineering, material science, and medicine. So if we have a little bit of a closer look at target station 2, it's made of a tungsten core, and it's wrapped in tantalum to give it some strength, and it's got these two cooling channels going once around one way and once around the other side. And what that does is, as you get this 800 mega electron volt proton beam coming in through the nose, it tries to take some of that heat away from it. This was designed to last for about 5 years. There's another model for TS1 that's engineered slightly differently. But what we're finding is that it's got an 18-month operational lifetime. And every time that there needs to be a change of the target, it's obviously a complex thing to engineer, but it's also has implications for the downtime. We have a whole suite of instruments that rely specifically on this target that are then unable to be used in while they change it over. And there's also a problem with radiological waste to deal with as well. So how does FEniCS come into this project? Well, I'm trying to use FEniCS to model the thermoelastic effects of our target. And I'm also using another program called Code Saturn, which is a French finite volume method particularly good for Navier-Stokes equations and to do the computational fluid dynamics for the cooling channels. The idea is that by doing this, we'll be able to contribute to a multiphysics code coupling library that'll allow us to hopefully quickly, efficiently couple the Code Saturn computational fluid dynamics to the FEniCS for the solid stresses, with a particular emphasis on portability, ease of use, and of course, because it's open source. So I'm going to talk a little bit about the breakdown of how I've gone through the process of doing this project. A lot of these steps are in there to make sure that I know how to use the software, that I'm using it correctly, and that the code is doing what I expect it to do. So I started with a simple 2D single material cantilever. And I took this particular test case from the Wolfram website. And what I did was, using that information from that test case, I then ran it through another finite element solver called Moose that I decided that I was going to use throughout the entire project as a consistent way of benchmarking. So I've got an idea from Wolfram about exactly what to expect, and then I'm doing it in parallel with Moose and FEniCS. what I found was through much trial and error, really good agreement between the displacement and also with the stress, with the only difference being with the von Mises stress, but through much deliberation, we think that that might be to do with moose more than to do with FEniCS. So we're looking into maybe doing some sort of ANSYS verification for the moose solutions. And our target is made from a welded tungsten tantalum mix. So the next obvious test case was to use a cantilever that was with two materials. This test case comes from the MathWorks website, uses Invar and copper. And so we were able to do again. We've got on the top our moose and then on the bottom our FEniCS. And again, we've got really nice agreement in the displacement. And also similarly with our tungsten tantalum beam. So the next obvious step is to move it on to then a 3D bimetal case. Which with the copper in bar, it started to make things a little bit different. You can see one is right above in the pictures, so you can sort of see the idea of what the difference in the displacement is. The stresses, though, if you see in this picture, you've got a really nice profile for the von Mises stress at the end of the beam there, where they've got that big temperature change. A less of a displacement with the tungsten tantalum, but still under investigation. And the stresses seem to have a real much better agreement than we've been working with. So the current step is to look into an experiment. We've got some experiment data from a chap down Wilcox, also at the STFC, who did that got some experimental data. He made a tantalum block, a tantalum-clad tungsten block, specifically to see whether the welding process was a big contributor to some of the stresses that were being seen in the block, and then subjected it to this proton beam at NGINX. So also at ISIS. So it's again been subject to that 3D, subject to that neutron beam. And I'm currently in a position where I am trying to model that exact situation with a simulation of that same block for some verification against those NGINX experiments. The next step will be to look at the heating and cooling cycle, because it's brought up to a temperature, kept there for about 2 hours, and then brought down. So I need to make it similar to that experiment. I'm also going to have to think at some point about moving my physical properties. Tungsten has a square relationship for its thermal conductivity. So then I'm going to be working with a nonlinear problem, start thinking about working with nonlinear solvers a little bit more. And then a very difficult side step is going to be thinking about the hardening process that happens when those metals are welded together, because they're actually brought beyond their yield point. And how I'm going to try and integrate that into my model. And alongside this, of course, is coupling with Code Saturn. So going back to the very original simple 2D single material block, we want to be having our heat profile coming in from Code Saturn, and then doing the displacements and the stresses in FEniCS, and running through each of those different steps by metal through to the NGINX, and then coupling my FEniCS beam straight to the straight channel conjugate heat transfer calculations. So here you can have a little bit of an idea of what I'm working with Code Saturn. You've got your temperature profiles in your solid versus your fluid, and how that distribution of heat is then being seen through the top surface of the tantalum on one side. Oh, I'd have done that wrong. So when we find that those previous steps are complete, we're hoping to have a thermoelastic model with the geometry of the target without the coupling, and then a full model with full target model with the thermal stresses to couple to the RANS calculations of the target and its cooling channels. And there's a little image video of our cooling channels there, and a sort of image of the beam pulse coming through the nose of the target. And with that, I bring myself to the end of my presentation. I thoroughly encourage anyone that has any tips or hints or advice for me or any questions to send me an email. And I'd like to give special thanks to Greg Cartland-Glover, my line manager. And if there's a couple of references there at the bottom from Wilcox as well. And thank you very much.